recently bought an oscilloscope, and so now I'm all high on building oscillator circuits. And so that was the last video, my first oscillator circuit put on the oscilloscope. But one of the oscillator circuits I'd like to build is a really simple one. I can't remember, it had a technical name like Pearson Anton or something, but you just put a cap in series with the neon bulb, and when the neon bulb turns on, it begins conducting, and it goes into what they say is an avalanche collapse. And so the capacitor discharges through the neon bulb, the voltage goes down in the capacitor, the neon bulb shuts off, the capacitor gets charged up. It happens again and again. The problem is the neon lamp turns on at somewhere between like 80 to 120 volts, and my power supply only goes at 50 volts. So how am I going to get to 100 or 150 volts to do this neon lamp oscillator? Now you could use a transformer, that makes sense, to transform the voltage, but generally those run off of alternating current, and my power supply is DC. So you could use one of the switched mode power supplies, you know, the flyback, the buck boost, the boost converter. The thing with those is they're not particularly linear. You know, you might put the power supply at 2 volts and you get 5 volts out. You put it at 4 volts and you get 20 volts out. So, you know, I want something that's 1-to-1. I want it where, you know, the power supply says 1 volt, you get 2 volts out. Put it at 10 volts, you get 20 volts out, or 1, 3, 10, 30. Just something straightforward and simple. So to do that, I've settled on using the approach that's used in the Marx generator, which is a very high voltage generating source, and just applying that concept through an Arduino to my DC power supply to see if I can extend the range of the DC power supply in the way that I'd like. So let's see what happens. So a Marx generator is a way of taking a DC input and getting a higher voltage DC output out. So we see a picture there that this is generally used for extremely high voltages. Sandia Laboratories has their Z machine, which I'm not going to get off topic, but that looks like something out of a science fiction movie. I like this because it's very intuitive and straightforward to understand what's going on. The circuit generates a high voltage pulse by charging a number of capacitors in parallel and then suddenly connecting them in series. So it's very simple and straightforward to understand, in the same way that you connect batteries in series and the voltage goes up. You can charge capacitors in parallel and then connect them in series and have a higher voltage, and that can be used as I said, to generate very high voltages. Now the way this is set up is not going to be exactly, I'm going to use the concept, but the way they set it up, I'll show you an example of someone who built an actual high voltage one of these, and you can see here it is built, and here's the circuit. So one reason I'm not going to do it this way is you start off with 4,000 to 6,000 volt DC input, and I don't have that. Like I said, I'm topped out at 50 volts. So, but we can understand this conceptually, and then I'll say what I'm going to do with the Arduino, is that you have a capacitor here, a capacitor there, and you can have a whole line of them. The capacitor charges up through 4,000 to 6,000 volts. They all charge up at the same time in parallel, and once they get to, say, around 4,000 volts, depending on how you set it up, you notice there's a gap here, so that's a spark gap. So at some point between 4,000 and 6,000 volts, you get a spark across this, or across one of them. As soon as, well, actually it should go across the first one. That's what this little part here is, to make sure it goes across the first one first. As soon as that happens, then now there's a higher voltage here, so this one sparks, this one sparks, this one sparks. Now you have all of those capacitors that were in parallel connected in series, And depending on how many stages you have, you go from 4,000 volts up to 40,000 volts or something like that. And because there's a 1 mega ohm resistor that you charge through, that's why that 1 mega ohm compared to the nearly zero resistance of the spark gap is why it's now in series. I mean, technically they're still connected in parallel, but each one is connected through 1 mega ohm. So you get a really brief spark, and then it charges up really slowly through the 1 mega ohm resistors. So I like this concept because it's very easy to understand, but there are a lot of drawbacks with it set up like this if you want to use this as something to increase the voltage on your power supply. So if you set it up like this with these 1 mega ohm resistors in place, then if you have a 1 amp power supply, then you can now put out a whopping 1/1,000,000th of an amp. So that's not going to work. But because you have an Arduino, you can make what I'll call a solid state. I mean, I guess the spark gap is a solid state version, I don't know. But you can make an Arduino version of this where you just charge it up, and then you have a switch where the 1 mega ohm resistors are, and then you break those switches and connect this switch. So that allows you to have the full amperage, however much you want to put through a resistor, but the full amperage going into your capacitors. So in a moment we'll go ahead and build that on the Arduino and transform some voltage. The last thing, they have giant versions of this. This is like some abandoned multi-story Marx generator from the old Soviet Union, just abandoned out in a field in Russia or something. So it's sort of like a dystopic science fiction novel or something, but it's very cool. So now let's build this contraption on the Arduino and see how it works, and see if it's going to be something that can practically be used practically to extend the voltage range of a power supply. So just to illustrate this concept before we build the circuit, I just have 2 caps on a breadboard here. I have a meter with just a random voltage, say 4.1, and the positive and negative are going into this positive bus line, this negative bus line. So right now I have a negative going to here and a positive out to the other leg, negative. So I've charged both caps to 4 volts. And if we put a meter on one of the caps, we see it's at 4 volts. And if we put the meter on this one, it would be at 4 volts as well. Now I've just removed the charging lines, and we see the cap is still at 4.07 volts, 007, but it's just charging slowly. It's a big cap through the resistance in the meter. Now if I move this leg, this part of the meter over to this leg, of course there's nothing there. However, if we now make a connection between the positive of this cap to the negative of that cap, it's just the same as if you connect the 2 batteries, positive and negative, and the voltage doubles. So if we connect that, and the voltage is 7.98, so it's doubled. So all we have to do is charge these things up, break all the lines, make a connection here, and you double your voltage. So to make this go, all we really need is a bunch of switches. And this is a opto-isolated relay. It's also called a solid state relay, and so it's really nice that you get the opto-isolation. And here's the data sheet for that relay. I'm not going to spend time on it. Just to point out, if I can find it, it's a 200 volt relay and can handle 0.7 amps. I shouldn't have to say this, I think, but if you actually get past 50, 60 volts, you start getting past the breakdown resistance of your skin. And so if you're out at 150, 200 volts, you can get an ouch or something worse, or it can kill you. So if you do something like this, be very careful and don't go out past 50, 60 volts unless you're comfortable doing so and know what you're doing. So if we go back to the relay, you see there's a dot there on one end of it. That dot is where, if you have a positive, say from like 2 to 4 volt or be 5 volt from the Arduino signal coming in, and negative there, it lights up an LED on the inside. And that LED then goes across an air gaps, hence the opto-isolation, and the light triggers a MOSFET or a transistor. In this case, I'm pretty sure it's a MOSFET on this end, and so everything's opto-isolated. So we're going to need 5 of these for this. So let's just first just see that we have 5 good relays. So this might kind of seem like overkill, but I find it's usually easier and faster and a lot less wanting to pull your hair out if you just test all your switches at the start. So I've just put all the switches in, and I modified the simple blink program to blink all the pins on and off, or in this case pins 8 through 12. So if we turn it on, and ta-da, we see 2 of them aren't working already. If I put my thumb on that one, so that one's just not settled in right. This one, however, is a problem. So going back to this one, this doesn't settle in right. And what I've found, and that's like a really common problem I run into with these solid state relays, is if you have put in like something with thick legs, like a transistor or something, it doesn't want to grab after that. The springs get deformed in here. And so the question is, do I rebuild all of this on a fresh breadboard, or just hunt around for a spot is what I'm going to do where it'll settle well. But this one, that isn't the problem. And so I just work my way back. So you see these LEDs will also light just from the signal from the Arduino. This is where you really should have a resistor, but it'll hold together long enough. So if we go to this pin, that's pin 11. We see that works fine, but if we move it over to pin 12, nothing. Yeah, it's not the connection to ground either. Move it positive to right to ground. So in other words, pin 12's fried. So at some point, doing higher voltage with inductors or something, I fried pin 12. So the very last thing is we know everything except maybe this switch is also fried. So let's put this switch in a good place and make sure that we have all good switches. So this is a decent spot to pause for a moment. So we have 4 of our switches in now, and we have a signal coming from, I think that's pin 11. So when that comes in, it turns this switch on that says power, positive power from the bus line goes through here, can go through the switch and put it out to there. That same trigger you see is going over to here and turns this switch on. So now the negative bus line can go through that switch out to here. So if we put a cap in there, when pin 11 goes high, that cap gets charged from your power supply. Now the same pin 11 signal is going out to here, to these 2 switches. Put a cap in there, and that charges up. So that one signal is saying charge your 2 caps in parallel. And so they charge up, and then all 4 of the lines break, and you just have 2 caps sitting there on the board. So the final switch will be to make a connection between the positive and the negative, either there to there or there to there. And then you have your series, and you've doubled the voltage. So now I've put in the last switch to make the connection in series between the negative here and the positive here. So let's change our little blink code so that it does what it should. So we have it like this now, but okay, so for our code, we'll put pin 11 high for a second, and that'll charge the 2 caps in parallel, and then we'll just shut it off, leave the caps there, shut it off for half a second, and then we'll put pin 10 high for 2 seconds, and that makes a connection between the positive and negative, and then shut that off and just see what happens. So I put the multimeter across the series connection there, and if we turn this on, we're at 1.8 volts. What do we see? We see 3.6 volts. So that 3.6 is when the connection is made across that switch. So as King Theoden said after the Battle of Helm's Deep, "We have victory!" But we're not done yet, because it's not doing anything yet. It's just kind of, you see that voltage. So what do we want to do now? Now, instead of these big caps, we want to put in small caps, and instead of it going once a second, we want to do this process thousands of times per second. That should cut down on, if I'm using the terminology right, ripple. And then we want to put the output of that series into a big cap. We'll use one of these, and if I'm self-taught, if I'm using the term correctly, that'll be a smoothing cap. And then you connect your load to the smoothing cap, and now you have double your voltage output. So let's see if we can do that to finish this off. Okay, turns out I spoke too soon. So if it's like that, it's working fine. Now you go to put in a cap so you can have something to draw a load off through. And what do we see happening? We see, okay, that was when it went high and it discharged into the air, got it up to 2.1 volts. That's good. And then kaboom, it goes back to 1.827. And so you can see when these two charge up in parallel, then you have the positive going out to here, and the negative of this one being charged up parallel is going to there. So every time these charge in parallel, it gets drawn right back down to the starting voltage. So that'll never work. I sing for you. My mistake. I have made my mistake. What a terrible mistake is this mistake that I have made. Monty Python, Mr. Neutron. Doesn't anyone have any culture these days? So what you need is one more switch. And so you can use the same timing as this one, but you don't want this thing seeing those caps when they're charging. So once we do that, I think we're good to go. Okay, so with the addition of that final switch, now we got it. So if I discharge this, we just see each time it's charging the cap up. Input is 1.8 volts, and it's charging it up past 1.8 volts to approximately double. It should be just about exactly double. So now we just, instead of doing that every couple seconds, we want to try and do it essentially as fast as we can. So now I've just grayed out the long part, and we just have it where it charges the two in parallel for 300 microseconds, shut them out, then they put it in series and let it go into the other cap for 300 microseconds, and then shut that down and start it over. So it goes 1,000 times a second. So now I've got the meter across our cap. We turn power on, 1.8 volts, 3.6. And the really beautiful thing is turn that up to 3.3, 6.5. It's just a one-to-one relationship. And so what you have now, you have instead of a 0 to 50 volt variable DC power supply, you have a 0 to 100 volt variable DC power supply. So just to sort of give some visual feedback, what I've done is taken an LED and put it across the positive and negative here. So the positive is going out to there, to a resistor, positive of the LED, the negative is going back to this cap. And I've also put an LED right across the bus lines of our input. So if we start to turn the voltage up here. You want to do this fairly slowly. Ooh, a little too high. So here we're at 1.1 volts. So there's 1.1 volts going in, and that LED's lit, that one's not. Go up a little bit further. So 1.5, it's lit more brightly. There at 1.7, they're both coming on. So 1.5 volts, 3 volts here. So it really is working. Well, we're now just about at 100 volts, and from the 50 volt power supply. But you can get rid of a lot of these switches, and that'll be the subject of the next video, is simplifying this with diodes. So again, that's my party trick. Turn a 0 to 50 volt variable DC power supply into a 0 to 100 volt one. So hope people might have had some fun, and take care everyone. Talk to you later. Bye.